I'm going to take you through the extension that's found in your textbook on pages 174 and 175, talking about how we take what we know about proportions and apply them to similar figures problems. I've just filled in the definitions, so you may want to hit pause and copy down those definitions before I get started on the examples. Okay, hopefully you got those definitions down. Congruent figures, okay, the symbol that we would use to indicate that two figures are congruent, we put an equal sign next to them and then with a little squiggly on top. The sign that we use to tell that two figures are similar, we put a little, just the squiggly, no equal sign. And corresponding parts really doesn't have a symbol that's associated with it. We're going to copy down a couple examples. So if I look over to the right-hand side of my screen, I see that I have triangle A, B, C. To create something that has the same size and same shape, I'm just going to clone what I have already, drag it down here, and we're going to label it to indicate that it is indeed a new shape. We're going to call this triangle D, E, F. So how would I write that ABC is congruent to DEF? Well, first I'm going to indicate that it's a triangle, so I'm going to use the triangle symbol. Triangle ABC is congruent to triangle DEF. It is important, because I started with A, that I also started with D in the second half of that statement, because A and D correspond with each other. So that's a preview. We're going to talk about corresponding parts down here. There are many other ways that you could have listed these correctly. Similar figures. Two figures are similar if they have the same shape, but not necessarily the same size. So I've taken that same triangle that we looked at. These two are congruent, and the relationship to this larger triangle is that they're similar. I simply took the same triangle and stretched it out to make it larger. So to write that statement, I would say that triangle DEF is similar to triangle JKL. Finally, for corresponding parts, we can have corresponding sides and corresponding angles. So I indicated before that the vertex A, we also have an angle in here. Angle A sits in the same spot or the same position so to angle D, so we would say that they're corresponding. I can also have corresponding sides. That's where I'm going to say that AB, this side length here, so AB, which is a line segment, it corresponds with DE. That means they're sitting in the same position. It doesn't necessarily mean that they are equal to each other, but it means that they're sitting in the same spot. Alright, let's go on to our next example. Talking about properties of similar figures. Corresponding angles of similar figures are congruent. So if I have a 90-degree angle here at C, I'm also going to have a 90-degree angle here at angle F. So I would say that angle A is congruent to angle D. I could obviously also say that angle C is congruent to angle F. And I could also say that angle B is congruent to angle E. So usually that's also going to be indicated above. So you can see I put in a right angle symbol for C and F. I'm going to put in one arc at angle A and indicate that that's going to be congruent to angle D. Angle B, I'm going to mark with two arcs. I'm going to do the same thing with E. That indicates that those angles are congruent. We're going to add some labels in here. I'm going to label AC as being 8 units long, AB, we're going to say, is 10 units long, and BC is going to be 6 units long. The second part of our properties of similar figures tells us that the ratios of corresponding sides of similar figures are equal. So it does not say that the sides themselves are equal to each other, but just that they are in proportion to one another. So therefore, if I took corresponding side lengths, like AC, which corresponds with side length DF, I would get a proportion of 8 to 4. You should all know that that reduces to 1/2, or 1/2. If I look at any other set or pair of corresponding side lengths, I should be able to get the same proportion. So if I look at, say, CB, CB is going to be 6 units long, and that corresponds with FE. FE is 3 units long. We know that that would also reduce to 1/2. I'm an idiot. This should be 2/1. Sorry about that, guys. All right, let's go to our next screen. So we can use similar figures to help us solve for unknown side lengths. Take a minute and label your two figures here. I'm going to put our side lengths in. Okay, so we're going to use the ratios of the lengths of corresponding sides to write a proportion. We're going to say that JK corresponds with QR and KL corresponds with RS. You should see that JK and QR sit in the same spot. It's helpful, obviously, that these two figures are facing the same direction. We're going to substitute in what we know about these things. We know that the length of JK is 18. The QR, that's what we don't know. That's our X. The length of KL is 8, and the length of RS is 12. We're going to use our cross products property to multiply 18 times 12, and that's going to be equal to 8x. I'm going to divide both sides by 8 to solve and get x equal to 27. So to answer the question fully, I would say that QR is 27 centimeters. I'm going to pause for a second, let everybody copy that down. The last example we're going to talk about, you already have written on your paper. I'm going to read it out loud. A man stands next to the Cape Hatteras Lighthouse in North Carolina. The lighthouse and the man are perpendicular to the ground. The sun's rays strike the lighthouse and the man at the same angle, forming two similar triangles. Use indirect measurements to approximate the height of the lighthouse. So I haven't given you any measurements yet. You're going to draw those figures, but first I wanted to kind of visualize it. What we have is we have the height of the man, and we have the height of the lighthouse. Those two things would correspond with each other. Obviously they're not the same height, but they're sitting in the same position. The man is going to cast a shadow, okay, and so is the lighthouse. And we know that those shadows are going to be cast at the same angle because the sun is hitting them at the same time. We can measure the length of the man's shadow, and we can also measure the length of the lighthouse's shadow. So there are our two triangles. So let's go back to our problem. Drawing in two triangles, let's take a minute. We had our man with his shadow, and we also had our lighthouse with its shadow. So take a minute and draw in two similar triangles. We obviously need to know some information to figure out what the height of the lighthouse is. The height of the lighthouse is what we're trying to find. The length of the shadow is going to be 83.2 feet. We also would need to know the height of the man because that would correspond. We're going to get that as 5.8 feet. And the length of his shadow, 2.5 feet. So we're going to write and solve a proportion to figure out what the height of that tower is. I see that 5.8 corresponds with h, so I put them over each other. I certainly could have put h over here in my numerator as well. That would have been equally correct. Because I put the height of the man in my numerator here, I'm going to put the man's shadow length, okay, in the numerator of my second ratio, and I'm going to put the length of the lighthouse's shadow in the denominator. To solve, I'm going to get 2.5 h is equal to 5.8 times 83.2. Obviously going to pick up my calculator to see that 5.8 times 83.2 is 482.56. To solve for h, I'm going to divide by 2.5. So the height of that lighthouse is going to be 193.024. So I'm going to approximate, it asked me to approximate, it's going to be about 193 feet tall. Okay guys, hope that helps. Thanks for taking your notes. See you Monday.